Welcome to class 10 of the course Transport Phenomena in Mesoscopic and Nanoscopic Systems. In the last class, we discussed about finding out the eigenenergies and eigenvectors or eigenstates of uh, two atoms which are located close to each other such that their wave functions actually overlap. Now, suppose we have a chain of atoms. Instead of two atoms, we have a chain of atoms, and the wave function from each of these atoms are overlapping with each other. And exactly as I stated, that it is due to this overlap that electrons can actually flow from one atom to the other, and this overlap basically decides what the conductivity or conductance of the structure should be. Okay, without this overlap, that is, if the atoms are located far away from each other, then there would be no current flow between two atoms, so there would be no electron flow between two atoms. And this kind of structure where atoms are arranged in a periodic fashion with same distance between them, this kind of arrangement of atoms is known as crystals. Okay, and it is this periodic arrangement of atoms that basically gives rise to electronic energy bands. Okay, an isolated atom has discrete energy orbitals or discrete energy levels. Whenever a chain of atoms come in close contact with each other, these orbitals mix up and they basically form energy bands. Okay, and in case of energy bands, we generally have a EK relationship, which we call dispersion relation. And you should keep it in mind that this dispersion relation is or this EK relationship is only a property of crystalline structures. Okay. Now, what is this EK relationship, or whenever we say that an electron in a K vector, then let me just clarify that what we actually mean by this term K vector. So, each of these atoms have an orbital associated with it, and if we find out the eigen energies of such a structure or such a combination of a chain of atoms, we will see that once we calculate the charge density would also vary in a periodic fashion. For example, let us say that the charge density here varies somewhat like this. This is only a illustrative example, not to be taken too seriously. Okay, let us say that the electron density in the case of this chain of atoms behaves periodically in this fashion. When the charge density is periodic, it basically means that the wave function also has a periodic property. Okay, it might not be periodic exactly in this fashion, but it has some periodic property. And when a wave function has a periodic property, we already know that it can be expanded in terms of the Fourier spectrum. Where this K0 is given by pi divided by L being the length of this entire lattice. And I am doing this for a simple 1D structure given here. Okay, and we know from our earlier discussion in the course on semiconductor device modeling that the highest value that k can have is actually pi by a. Okay, so this actually doesn't in real structures or real devices. This does not run from minus infinity to plus infinity, but it has some definite limit. So the maximum value of nk0 for a given band is basically pi divided by a, and this is also where the concept of the first Brillouin zone comes into picture. Okay, if you go beyond this pi by a, we will have the second band or the band above that. Okay, so let me reframe it here. And n is of course an integer. So when we talk about k vector, it is exactly this k vector we are basically talking about. So it is a kind of the Fourier component of the electron wave function, overall wave function, or the overall eigenstate, or the Fourier component of the charge density. Okay, normally when we are talking about state, we generally mean the Fourier component of the eigenstate or the eigen wave function. Okay, so we know two things here, that whenever this chain of atoms comes together in a crystalline structure, the charge density, the wave function would have some periodic property. And the second thing that we know is that this kind of structures have a definite ek relationship, and the k here is basically the Fourier component of the wave function or the Fourier component of the charge density. Okay, so let me show here that if the Hamiltonian is given by an expression like this, then the matrix in space basis, the matrix corresponding to the Hamiltonian in space basis can be represented in tridiagonal form. Okay, so normally note that here we have assumed a simple expression for this potential V, but generally in real structure, this V is what makes the Hamiltonian and the eigenstates unsolvable. Okay, and it might not be possible for you at this moment to understand fully that how complicated this term is, particularly the electron-electron interaction, because we will not go into too much detail, but the purpose is just to give you a brief idea of the generic formulation. Okay, but just know this, that this term is something which creates the maximum amount of trouble in solving the Schrodinger's equation, and particularly the electron-electron interaction term, because the electron nuclear repulsion is not that much complicated, because the nuclear position is fixed. The nuclear repulsion is also not that much complicated, because again the position is fixed. But it is the electron-electron interaction, because we do not know what is the wave function of the electron, so we cannot calculate the electron-electron interaction, and without the electron-electron interaction we do not know what the Hamiltonian is, so we cannot also solve the wave function. So that kind of problem is there. Okay, so it creates a self-consistent situation, and because the wave functions over which we can search is actually kind of infinite, or the set of wave functions over which we can do the search of the actual eigenstate is actually infinite, it basically creates a problem where we have to basically move or hover over an infinite set of wave functions to actually know what are the eigenstates of the system. Okay, that's a very crude definition of the problem, but it can be sophisticated more and more, and with the help of some theory and some approximation, people have sophisticated things to a large extent, so that we can actually now calculate the properties of various structure, crystal structure, using powerful computers. But just know that this is the term which creates most of the problem in solving the Hamiltonian of the entire system. So here, for simplicity, we will actually assume that V is a constant, not constant, but V is a well-known function, or we can also consider it as a constant, because my purpose here is actually to show you the methodology and not go into the approximations and various techniques used to approximate things. So let us first see what this term delta this del square is, inverted delta square, which is the square of the gradient or the Laplacian operator. Okay, so let us first do it in 1D. So in 1D, this term basically becomes del 2 del x2, and now what is this del del x? So this is limit h tends to 0 plus. So let us just write it as psi. So x plus h minus psi x divided by h, and if the function is continuous, which of course wave functions should be, then it is also equal to the left hand limit, or we can write it in other way also. We can actually write it like this: delta x tends to 0 plus, and x plus delta x divided by delta x, and here delta x tends to 0 plus, x minus delta x, because I am now calculating the left hand limit, so x minus delta x minus psi x divided by h. Okay, now this del 2 psi x del x2, this is equal to limit delta x tends to 0 del psi del x, x plus delta x minus del psi x del x divided by delta x. So this limit should be here. Actually, for this expression, it should be psi x minus psi of x minus delta x. Okay, now for this expression, I will use this left hand limit here, because the left hand limit is actually the right hand limit. I could have used this expression as well, but for the purpose that would be clear just now, I would use this form for this term and this form for this term, just to get a particular form of expression. Okay, so this is equal to limit delta x tends to 0. So if I use this form for this expression over here, it would readily become psi x plus delta x minus psi x divided by delta x square minus, so the entire thing is within this limit, minus I would use this expression for this term over here. Sorry, for this one also I would be using this expression over here. Okay, so minus psi x minus psi x minus delta x divided by delta x square inside the limit, which is equal to limit delta x tends to 0 psi x plus delta x minus 2 psi x plus psi x minus delta x divided by delta x square. Okay, so this is basically our del 2 psi x del x2. Now what we have here is basically minus h cut square by 2m del square plus v. So h psi, so h is an operator, the Hamiltonian is an operator, not just a number or function. This is equal to minus h square by 2m delta square psi plus v psi. Okay, so we are working in one dimension right now because it is easier for us to understand. Okay, so what we have here is basically so if we are working in one dimension, it is just del 2 del x2 psi x. So what we have here is basically minus h square by 2m delta x square psi x plus delta x minus 2 h cut square by 2m delta x square plus v psi x minus, not minus, plus sorry, this one should be plus over here because a minus is already present, so this one should be plus, and yeah, a minus h cut square by 2m delta x square psi x minus delta x. Okay, of course in the there is this limiting condition that delta x tends to 0, but here we are not putting that limiting condition, but what we will do is we will basically divide our wave function. So this is the axis x, and then we divide this, the wave function is present, so like this, let us say, and we divide this axis into very tiny fragments of width delta x. Okay, okay, and now instead, earlier when we actually derived the eigenvectors and eigenenergies of the two atom system, we basically used the orbital basis. Now we are not using the orbital basis, but we are using the position basis. Remember that the Hamiltonian can be written in many bases. It can be written in energy space when the Hamiltonian is basically a diagonal matrix. It can be written in the momentum space, it can be written in real space, and it can be written also in the orbital basis. So depending on which basis you use, your form of Hamiltonian would basically change. Okay, but at the end things would come out to be the same if you have done your calculations correctly. But uh, you can express the Hamiltonian in many bases, and we generally employ one or the other basis depending on the situation at hand. For some situation, using one basis is more easier than the other. For example, in the two atom system, it is really difficult to use the basis of momentum eigenstates, because the system is not periodic. So momentum basis or momentum eigenstates really does a bad job in approximating the wave function or the eigen function of the system. Okay, if the system would be periodic, if the wave function would be periodic, in that case momentum eigenstate would be a good basis to study the properties of the system. But in this case, because the system is not periodic, momentum eigens space or momentum basis is really a bad tool to compute its properties. Okay, so here instead of writing it as psi delta x, we just name the point as 1 2. So this is point number 0, point number 1 2 3 4. So let us start from 1 actually, instead of, so this is point number 1, the origin, then this is 2 3 4 5 6 7 8 and etc., and we represent it as psi 1. We are using the space basis now, psi 3 etc. Okay, so when we compute this h psi, if we use the position basis or if you use the real space basis, then h of psi n is nothing but minus h cut square by 2m delta x square psi n minus 1 minus plus h cut square by 2m, 2h cut square by 2m actually, so h cut square by m delta x square psi plus v psi n minus h cut square by 2m delta x square psi n plus 1. Okay, this is a generalized equation. Of course, the equations are going to change towards the end points, that is at point number 1 and point number n over here. Okay, so we call this term minus h cut square by 2m delta x square as t0. So this equation then becomes h psi n equal to minus t0 psi n minus 1 plus v plus t0, 2t0 actually, psi n plus minus t0 psi n plus 1. Okay, so in this way we can write the equation, and we will assume a periodic boundary condition, which basically means that this nth point is actually connected to point number 1, okay, in a circular loop. Okay, this is the boundary conditions which we often use to evaluate system, and it basically makes our calculation easier. But if we are actually solving a large system, it doesn't matter whether we use periodic boundary condition or any other boundary condition. At the end the result would be the same, but periodic boundary condition basically helps us to simplify the calculations of our system. So we'll assume that this end point is connected to this first point in a circular loop like this. Okay, so our equations basically become h psi 1 equals to minus t0 psi n plus 2t0 plus v psi 1 minus T0 psi 2 for 2 less than equal to n less than equal to n minus 1, we have h psi n equals to minus T0 psi n minus 1 plus plus 2T0 plus v psi n minus T0 psi n plus 1. Okay, and for n equal to n, this is for the top one is for n equal to 1. For n equal to n, we have h psi n equals to minus T0 psi 1 plus 2T0 plus v psi n minus T0 psi n minus 1. Okay, so we have n variables here, n components of the wave function. I again repeat that we are writing these equations in the real space basis. Okay, psi n is the wave function at the nth point. It is not the wave function corresponding to an orbital. It is not the wave function corresponding to a momentum eigenstate, but this psi n is basically the wave function value at the nth point. So this is we are using this basis we are using is real space basis. Okay, so now we have n variables actually. So what are the variables? So the variables are which we do not know are basically psi 1 psi 2 dot 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 psi n, and these are system of n linear equations. Okay, so when we have n variables, so total n variables and in system of linear equations, we are able to solve for the variables. And if we write this all these equations in matrix format, what will we get? So we'll basically get so our equation is basically h psi equals to e psi, and we have discretized this equation in a position basis, in a real space basis by writing the equations in this format. So this discretized version of this Schrodinger's equation basically now becomes, let me draw the matrix over here. So these are the points 1, 2, 3, 4, 5 and n. So minus t and then 0, 0, 0 and this one is minus t, t0. So this is the equation for psi 1. So this is the wave function. This is the equation for the wave function at the nth at the first position. Then the equation for the wave function at the second point or the second position is basically minus t0. So on this side we have the wave function in the real space basis, that is psi 1, psi 2, psi 3, psi 4 and all the way up to psi n. To t0 plus v minus t0 0 0 minus t0 to t0 plus v minus t0 0 0 0 0 minus t0 2t0 plus v minus t0 0, and at the end, so then this system would continue. This is an n cross n matrix. Let me write it here. N cross n matrix, and then the last equation is for psi n, which is minus t0, then 0 0 0, the fifth position is also 0, the n minus 1 position is let us basically give this to the n minus 1th position actually, because it is necessary, not the fifth position but the n minus 1, n minus 1. So the n minus 1 position is minus t0 and nth position is 2t0 plus v. Okay, so you see that the Hamiltonian can be written in this case in a tridiagonal format. Okay, so there is one diagonal column. So let me just highlight it here. So this is our diagonal column. All the elements in the diagonal column are 2t0 plus v. This is the diagonal column of the square matrix, and this is the upper of diagonal, and then it would continue basically, and this one is basically our lower of diagonal, and all the elements outside these three main diagonal and these two off diagonals are basically 0, except because of periodic boundary condition we have this t0 over the corners here. Okay, so what I mean to say here is that in case of a periodic system we can write the Hamiltonian in a tridiagonal format. So this is our matrix representation of our Hamiltonian H. Okay, and H psi is equal to E psi. So when we write the entire Schrödinger's equation in discretized format in real space basis, it basically becomes H psi equals to E psi. So psi 1, psi 2, and then all the way up to psi n. So finding the eigenvalues of this system corresponds to finding the eigenvalues of this matrix equation, and finding the eigenvectors of the system or the eigenfunction of the system corresponds to finding the eigenfunctions or eigenvectors of this matrix equation. Okay, so I hope I have convinced you that in case of a periodic system, the Hamiltonian can be written in a tridiagonal format. Okay, now we'll assume that the Hamiltonian can actually be written as a tridiagonal format and proceed from there. So there are a few things that I would like to point out in this discretized version of the Schrödinger's equation, so as to convince you that this thing actually works. So let us consider our Hamiltonian H, the discretized version of our Hamiltonian. And as we said earlier that this can be actually be expressed in a tridiagonal format. So this is the wave function at position 1, the wave function value at position 2, 3, 4, and up to n minus 1 and n. And this first row is the equation corresponding to the wave function at the first position, The second row is the equation corresponding to the wave function at the second position. The third row is the equation corresponding to wave function at the third position. And then at the end comes the n minus 1th position and then the nth position. Okay, so this just as we have written before, minus t0 to t0 plus v and no, this is for the second equation. We could have written it as t0 minus t0 to t0 plus v t0 and then 0 0 0, but we would really like to make it compact, so we would write this t0 as ess, which are the off diagonal terms. This is minus, and we would like to write this one as E0. This is basically known as the self energy of the system. Not this exact quantity, but self energy is a more complicated term, so let's not discuss it here. So I just want to tell you that we would write this minus T0 as ESS and this 2T0 plus V as E0. Okay, so that would make our representation simpler. So let us write this entire thing. So the first equation is E0 ESS 0 0 0 ESS. The second equation is ESS E0. So we also have this our eigenvector over here. And then this n minus 1 equation basically becomes 0 0 0 0 E0 ESS and ESS 0 0 E0. Okay, this is equal to E times psi now. You already know that in a periodic system, this k states or a wave function of the form e to the power ikx basically satisfy the Schrodinger's equation. This is for a periodic system or a crystalline system. Okay, so in a crystalline system, you already know that energy bands form, and in those energy bands there is a dispersion relation or EK relation. So we already know that the wave function for the kth state. So in this case, the momentum eigen basis or eigen functions are good components to represent, or good basis to represent the entire system. And so the kth component can be expressed as psi kx equal to a e to the power ikx. Okay, so if we discretize this wave function, we would have basically psi n, or not capital N but small n. So it is the value of the wave function at the nth point. So this is equal to a e to the power ik x is equal to n delta x. So for the time being, we would just assume that delta x is basically spacing between two atoms. which is represented by A. So psi n can be represented as A e to the power I k n A. Okay, so write n as the suffix here because it is for the discretized case. So now let us pick up a random equation from here, from this matrix. So if we pick up a random equation from this matrix, we would basically get ESS psi n minus 1 plus E0 psi n plus ESS psi n plus 1 equals to E psi n. Now we basically replace all these values by this equation over here. Psi n equal to A e to the power I k n A. A is basically the normalization constant. So since we have this all these psi n's over here, this A basically cancels out. So I will not be writing this A anymore. So we have then ESS e to the power I k n minus 1 plus E0 e to the power I k n A plus ESS e to the power I k n plus 1 A. This is equal to e to the power I k n A, and we get E equal to E0 plus ESS ESS e to the power minus I k A plus e to the power I k A, which is equal to E0 plus 2 ESS cos k A. Now if k A is much less than 1, we then recover then this cos k A is approximately equal to 1 plus k square A square, sorry, 1 minus actually k square A square by 2. So what we get is E equal to E0 plus 2 ESS minus ESS k square A square by 2. So we recovered this parabolic EK relationship. Okay, that this energy, the eigen energy, is basically proportional to k square. Okay, now the second thing is that we have also shown that a wave function of this form basically satisfies our Hamiltonian, this discrete version of the Hamiltonian, that is this Hamiltonian. Okay, so we have already proved that we have basically seen three things. That the first one is that a Hamiltonian for a periodic system can be expressed as a tridiagonal matrix. The second thing is that a wave function of this form basically satisfies, or a wave function of this form is the eigen state or eigen function for the Hamiltonian in this case, in case of a periodic crystal. And we have recovered this parabolic EK relationship for our dispersion relation. Okay. Now you may ask me the question that what about this A square, because it appears that this energy, the allowable state or the eigen energy, is basically proportional to A square, which is basically the lattice spacing that we have taken. We have taken this delta x to be equal to A square, A, which is the lattice spacing. Now you may ask the question that is it really dependent? Or you may ask the question that it appears that if I basically vary this delta x, then I would basically get a different value of eigen energy, because uh, this is this is my delta x square actually, which I have taken to be a square. But if I vary this delta x square, if I take it instead of delta x to be a, if I take this delta x to be a by 2, let us say, in that case will this eigen energy vary? So the answer is of course no, because actually this ESS, remember that what this term ESS is basically. So ESS is basically minus T0, and which is equal to h cut square by 2m delta x square. Okay, so this delta x here and this a square, which is actually delta x square, these two actually cancel each other. Okay, so this entire term is not dependent on the discrete spacing that we take. This is the first point. The second point is basically that this term is basically also independent of this delta a square or delta x square. Remember what this term E0 was. This term E0 was 2T0 plus V, and this one is equal to minus 2T0. So this T0 basically cancels out. Okay, so this term is basically proportional to the external potential. Okay, in reality it is not only proportional to the external potential, but it also depends on the electron-electron interaction. But I mean, in this case at least, because we have taken the Hamiltonian to be simple, this term basically depends on the potential. Actually, V might not be the external potential. V might also I mean come from, of course it contains a component of electron-electron interaction, and it also contains electron nuclear interaction and it also contains nuclear interaction. Okay, so V is the just the, let us call it the potential. So it depends on your potential, or if I would say that effective potential. Okay, so I would also urge you to basically look at this term over here. So let us write this term in a different fashion. So the eigen energy is basically ESS e to the power minus IKA plus E0 plus ESS e to the power IKA. Okay, now remember that here we have taken the atoms to be our lattice points, and if we are to solve the eigen energy directly, so this is semi-infinite both in the left and the right direction, so this is an infinite arrangement of atoms. Okay, so let us this one, the wave function is written as n minus 2, n minus 1, n plus 1, n plus 2, and so on. Okay, now if I were to find the eigen energy of the system, it is actually, from this equation we can draw a conclusion, of course intuitively. I will not prove it here, but it is enough to solve an equation of this form: E psi 0 equals to h k psi 0, where k is a vector now, because we are talking about real lattices or real crystals in 3 dimensions, where hk basically has this form: summation over m h nm e to the power I k dot dm minus dn. Okay, so basically let us take an example here. If this equation is difficult to understand directly from this equation over here, So let us talk about a two-dimensional lattice, because three-dimensional is difficult to describe here. So let us say that we have a periodic arrangement of atoms like this in a rectangular fashion. And we'll just consider the next nearest neighbor. So if we are considering this atom over here, which atoms are the nearest neighbors? So this atom, this atom, this atom, and this atom are the nearest neighbors. This atom is slightly far away. We can consider it in a more complicated model, but let's not move into more complications over here. So the position of this atom, okay, let us call it dn, and the position of this atom is let us call it d1, d2, d3, and d4. So these are all vectors. So we can find the eigenenergy E by this equation over here. I have already written the equation, where this hk, this is not Planck's constant. Okay, this is kind of a representation of the Hamiltonian, but since we are this is an equation, we are not writing it like the operator h over here. Okay, but this is a representation of the Hamiltonian in equation format. Okay, so hk equal to sum over the nearest neighbors 1, 2, 3, 4 hnm. Hnm is nothing but, let me write it here. So this is in its space. So in Kate notation, it is just NHM. Okay, so summation of 1, 2, 3, 4, and let us call that this term is basically minus T0 for the next nearest neighbors, minus T0 for next nearest neighbors. Then summation of 1, 2, 3, 4 minus T0 e to the power I k dot, and then let us say that this lattice constant is a. So this is a x cap, this is minus a x cap, this is, let us call it a y cap, and let us call this minus a y cap. Okay, these vectors a x cap, and this one is minus a y cap, the vector. Okay, so e to the power I k a let me a k dot x cap plus e to the power minus I k a, sorry, I a k dot x cap plus e to the power I a k dot y cap plus e to the power minus I a k dot y cap. Okay, so this entire thing is equal to, so we don't need to write the summation now because we have included all the terms. So this is only minus T0 minus T0, then this one and this one gives us a cos term. So 2 cos kxa, and this one and this one again gives us a cos term. So this is 2 cos kya. Okay. So you can also get this equation for a one-dimensional lattice if we use this equation over here. Okay, we will see more examples so that it is clear to you. Okay, so let us do up to here today. Thank you everyone.